In this PowerPoint, we're going to talk about hypothesis testing. So hypothesis testing is one of the most important ways we create studies, research studies, and it really is working on this whole concept of inferential statistics, right? And it's going to help us decide if, effects actually occurred, if our treatments actually had any, effect, good or bad, if any kind of groups differ from one to another, and then if one variable can accurately predict another variable. So hypothesis testing is one of the most commonly used inferential procedures. So again, up until this point, we've been talking about descriptive statistics. Now we're going to kind of move closer into inferential statistics. And the definition is that hypothesis testing is a statistical method that uses sample data in which to evaluate a hypothesis about a population. So again, we're going to do something to a sample, give them new medicine, try a new therapy treatment on them, test them at different altitudes, and then we're going to evaluate that and say, okay, is that now, can we infer anything that we learned from that sample back to that population? Okay. So how does this work? Well, you have an idea. You have an idea that something happened or something might happen. So you're going to create your hypothesis, and hypothesis is just a fancy term for a testable prediction, right? And so something might be happening, might be sounding like groups are different from one another. So why are they different from one another? Or can I make them different from one another? Some treatments have an effect on an outcome that's measurable, right? Or one variable can accurately predict another variable. So when we're testing hypothesis, you have two possibilities, and they're not overly complicated. One, nothing happened, right? Or two, something happened. And that's it, right? When you test a statistical hypothesis, you're trying to see if something happened. And you're comparing that something happened against the possibility that nothing happened or that nothing should have happened. Okay, so the first one we have here is a null hypothesis, right? And so null hypothesis is just a fancy name for nothing happened, right? So null, like thinking like nothing, zero, not a bupkis zilch, right? You didn't find an effect. You didn't find the groups to be that different from one another. Your treatment doesn't seem to help anybody, or your variables are not related, or you can't predict one variable from another. The alternative for nothing happened is something happened, and this fancy name for something happened is just your alternative hypothesis. Or there was an effect of your treatment. Your groups are different, or one variable can predict another variable. Okay, so here comes the counterintuitive part. We're going to try to disprove the null hypothesis, because if we can disprove that nothing happened, then we can say that something happened, right? But it's very backwards whenever we say it in English, right? So you kind of have to learn this statistical logic of trying to prove or disprove that nothing happened. Okay, so we have 4 steps in the hypothesis testing. Number 1, we're going to state the hypothesis. And you're going to do it in those pairs, right? So you're going to have a null hypothesis and an alternative hypothesis. Number 2, set the criteria for your decision, right? So how high do you want to have that watermark? How high do you want to have your numbers be that would beat that null hypothesis? Number 3, you're going to collect data and compute the sample statistic, right? So again, thinking back to previous chapters, computing, the distribution of sample means, you're going to find that Z for that group, right? And then 4, make a decision, right? Did your sample mean, was it statistically significantly different than that null hypothesis? Okay, so how we notate a null hypothesis is H, and then down right below it is an O, right, or a 0. And the null hypothesis states that in general population, there's no change, no difference, no relationship. So how does that sound in actual study? You would say the null hypothesis is that room temperature has no effect on exam scores. Okay? The alternative hypothesis would then be that there is a change, a difference, or relationship in the general population, or how you would say that in a research study. And the alternative hypothesis, there's a couple different ways you can notate that. I was taught HA, but I think Graviter text, Aaron text uses H1, right? So either one. So null is HO usually, and H1 or HA for alternative. So it'd be alternative hypothesis is room temperature does have an effect on exam scores. Number 2, set the criteria. So what you're going to try to do is you're going to try to figure out, okay, we have a couple different options here. In the distribution of sample means, you're going to have some that is likely to occur if that null hypothesis is true. And the opposite is those that are very unlikely to occur if the null hypothesis is true. Your alpha level, right, or level of significance is the probability value used to define very unlikely. And you can, as a researcher, set your alpha level at whatever you want to. 0.05 is the most common for social behavioral sciences, but I have seen 0.01, 0.1, 0.025, right? And that alpha level is going to set the critical region. And the critical region is composed of the extreme sample values that are very unlikely to occur just from chance alone. Right? And these boundaries of the critical regions are determined by that alpha level. Okay, so alpha is denoted with this Greek letter A, right? So alpha level. So let's take a look here. If a scientist sets her alpha at 0.05, she's willing to accept the probability that there are 5 chances in 100 that the results that she obtained are just due to chance alone. Right? So take a look at this sampling distribution up here, right? This is like the fail to reject zone, this yellow, right, the lighter side. This is your alpha level, 0.05, and this alpha level creates this critical region right here as noted in blue, right? So if you run your analysis and you say, I believe if I teach the children how to read by whole word reading, I can, greatly increase their reading ability scores. And you run the semester and you have them learn how to do whole word reading versus phonetic reading. And at the end of the semester, you test them on their reading ability, and they have an average score, right? The sample mean. So think back to last chapter when we did like the distribution of sample means. So if their sample mean falls in this like yellow zone or the safe zone, right, your new teaching method wasn't that effective, right? But if your sample mean falls in this critical region as set by the alpha level, you can say that, well, I'm going to reject that null hypothesis because my teaching whole word reading is very effective, right? So if your test statistic is outside the alpha's cutoff score, right, usually in the tail, and you can have one tail or two tail, what you're going to say, you're going to reject the null hypothesis. And if not, if it doesn't reach that level of extremeness, right, you're going to say you're going to fail to reject the null. You never say I accept the null. You just say I fail to reject the null hypothesis. Okay. So the previous slide showed a one tail. This is a two tail now. So we're going to have a z-score of 1.96. And if you look up in your unit normal table, z equals 1.96, you'll see in that in the tail column, right, that it refers to 0.025 in each tail, right? So what we're doing here is if you set your alpha at 0.05, right, you'd have 5% chance that, one tail. But since it's a two tail, we have to split the alpha. So 2.5 on this side and 2.5 on this side. So you would look up and 2.5% when you convert it into a decimal is 0.025. 0.025 gives you a z of 1.96. And again, that unit normal table, you can read it back and forth. You can read it left to right and right to left. And when we talk about unlikely outcomes or extreme outcomes or statistically significant outcomes, we're usually talking about that 5%. And again, it can be 5% all in one tail. And I'm going to go back up one slide, right? So we can say, oh, this alpha 0.05 is all in this one tail, or it can be in two slides. If it is in two slides, you have to split the alpha. So 0.05 becomes 0.025, or 5% becomes 2.5%. And if I look up 0.025 in my unit normal table, I get 1.96. So now, this critical region, right, 2.5%, correlates with a z-score of plus or minus 1.96. So my sample mean has to be greater than positive 1.96 or less than negative 1.96, and I can reject the null. If it doesn't, if my sample mean falls somewhere in here, I have to fail to reject the null. Okay. These are some common alpha when you split it, right? So alpha 0.05. When you split it, becomes alpha 0.025 because again, we're going to split half on this side and then half on this side, right? So we have alpha 0.05 split becomes alpha 0.025. You look up alpha 0.025 in the unit normal table and you get 1.96. Okay? Now, when we make the alpha harder, right, when we make it more stringent or smaller, right, we go down like 0.01. If you split it, now it's 0.005, or in a Z, 2.58. To get even smaller of a critical region to hit, 0.001 becomes 0.0005, right? And the Z to beat now is 3.3. So again, as we're making that tail smaller, right, we're making that region tighter, it becomes harder and harder to reject the null. So the only reason you would make your alpha so tiny, and that critical region so tiny, is if you are really sure that your effect, that your treatment has an effect, or that you know you can reject that null. Okay. Number 3, you're going to collect the data and compute the sample statistic, right? You have to collect the data after the hypothesis is stating and after you set the criteria. If you don't, it's like considered phishing, or it's really frowned upon, because this sequence assures the objectivity. So I'm going to say, this is my hypothesis, this is the mark I have to beat. Now let's run the statistical analysis and let's check our decision. Okay. Number 4, make a decision. If the sample data are in the critical region, the tails, the null hypothesis is rejected, and we state the results were found to be significant. Okay? Now, significant only means that the effect of the result was not due to chance alone, probably. Now, we do have sometimes we talk about errors, and we'll talk about type 1 errors and type 2 errors a little bit later in the lesson. But what you're saying is, say you set your alpha at 0.05. What you're saying is, if my sample data, right, fell in that critical region, 0.05 or that 5% area, I am 95% sure that they're there because of the effect of the treatment, right? Not just because of chance alone. Right? But if the sample data are not in the critical region, the researcher fails to reject the null hypothesis. And again, we never state that the null hypothesis is accepted or retained. We just say that we fail to reject the null hypothesis. Okay, so think about null hypothesis like a trial, right? So a trial begins with a null hypothesis. In America, you are innocent until proven guilty. And the police and the prosecutors, what they do is they gather evidence, data, to reject this innocent plea and conclude your guilt. Right? And if there's sufficient evidence, the jury rejects that innocent claim, the null hypothesis, and concludes guilt. But if there's not enough evidence, the jury fails to convict. But that doesn't necessarily mean that the defendant is innocent, right, or that your stuff didn't work. It just doesn't mean that you can't prove it. Okay, so let's take a look here. So a researcher begins the population, in this case scores on a standardized test, with scores normally distributed with a mu of 65 and a standard deviation of 15. The researcher suspects that special training in reading skills will produce a change in the scores for the individuals in the population. So a sample of 25 individuals is selected, and the treatment is given to that sample. Following the treatment, the average score for this sample is 73. So mean 73, right, versus the mu of 65. So the question is there evidence to suggest the training has an effect on test scores? We want you to use an alpha of 0.05. Let's go through the steps. Okay, again, mu 65, standard deviation of 15, and mean of 73 with 25 people in the study. So the null hypothesis is mathematically mean equals 65. In English, special training in reading skills will not produce a change in test scores. So mathematically, pretty short and simple. Mean equals 65. But in language, like if you're going to say it, right, you'd say something about, will not produce, there will not be, things like that. And have that no or not word in there. The alternative hypothesis mathematically is just that mean does not equal 65, or that special training in reading skills will produce a change in the test score. So you're going to have something different besides 65. You could have higher than 65 or lower than 65. Okay. So the first thing we need to do is find Z obtained. And OBT just stands for obtained. Right? This is like your last chapter we talked about determining the z-score for like a sample statistic, that's what we're doing. Okay. So first thing you need to do is find the standard error, standard deviation divided by the square root of the sample size. In this case, 15 divided by the square root of 25, or 15 divided by 5, so 3. And then put that standard error in the numerator or the denominator part of your z. In this case, we're calling it z obtained, right? So mean minus mu divided by standard error, or 73 minus 65 divided by 3. So our z obtained is 2.67. Okay. So now let's figure out the critical region. Okay. So get out your unit normal table and go for alpha 0.05, but again, we're having a two-tail, so you need to split it. So look up alpha, or look up tail 0.025. And you should see, when you look up in the unit normal table, in the tail 0.025, you'll see a z-score of 1.96. The p-value, we'll talk about p-value a lot later on, right? It's having to do with like research reporting, so you'll see this in academic journals. Okay, so is this significant? So if it is significant, you're going to write all your results in the appropriate statistical format. Okay, we're going to use APA, right? So you're going to use your alpha and your p-value, your z obtained, and your z crit. Okay, so the answer is yes. We did find that special training did produce a change in math scores. So we're going to say is we're going to reject the null hypothesis as our z obtained equals 2.67, which is greater than our z crit, that critical region of 1.96, with a p-value being 0.0038, alpha being set at 0.05. So let's take a look at what this looks like graphically. Okay, so we have a two-tailed test, right? And this is our fail to reject zone, and we have two critical regions. So we had alpha set at 0.05, 2.5 on that side, and 2.5 on this side. If you look up in your unit normal table, 0.025 in the unit normal table, it'll give you a z of 1.96 because this is a two-tailed test. You're going to have a negative 1.96 and a positive 1.96. That's our z crit, right? Our critical value of z. And our z obtained, 2.67, is larger than 1.96, right? Because 2.67 is bigger than 1.96. So, yay, we get to reject the null hypothesis because our z obtained is larger than our z crit. Okay, so uncertainty and errors. So hypothesis testing, again, is an inferential process. And because it's inferential, we aren't dealing with the entire population data. Errors are possible, right? It's also, its uses are limited to information to reach a general conclusion, right? So sometimes it's not going to be able to be inferred to a bigger population. So let's talk about errors. Type 1 error and type 2 error. So type 1 error is a rejection of the null hypothesis when the null hypothesis is true. Or in other words, you're going to say things are different when they're really not. Okay? So you're going to say, yeah, my medicine totally made them feel better, and it really didn't. Or my new teaching strategy was very effective. It wasn't. Setting a stringent lower, so going from like 0.05 to like 0.01, decreases the risk of committing a type 1 error. Type 2 error is retaining the null hypothesis when the null hypothesis is false. Or in other words, you're going to miss that relationship, miss that ability to actually prove that your stuff works usually because you set your alpha level too stringent, right? You set it at 0.001 and, I don't know, set it at 0.05 and you would have been able to say, yes, it really works. Because with a type 2 error, what you're saying is, my medicine really did work, I just can't prove it, right? My new teaching strategy was very effective, I just can't prove it with this study. Run it again, lower your alpha, and you'll get around that type 2 error. Okay, so take a look here. True or false? A type 1 error is like convicting an innocent person in a jury trial. True. Innocence is that null hypothesis, right? Conviction is rejecting that null hypothesis. Okay. True or false? A type 2 error is like convicting a guilty person in a jury trial. So think about this one. It's a little bit tricky. Type 2 error is like convicting a guilty person in a jury trial. No, this isn't an error at all. You should convict a guilty person in a trial. Okay. A result is significant or statistically significant if it's very unlikely to occur when the null hypothesis is true. Okay, in other words, the result is sufficient to reject that null premise. Okay? So in APA formatting, you're going to state the significance, right? You're going to report the value of the test statistic, your z obtained, right? And you report the alpha level or p-value, your 0.05 or your 0.0038 in our example. Okay. So in the previous test, we did a two-tailed test. We're going to run that exact same test again, but this time we're going to run it as a one-tailed test. Okay? Because researchers usually have a specific prediction about the directionality of a treatment, right? Researchers aren't going to invent a medicine that increases depression or increases anxiety. They're looking for a medicine that will decrease depression or decrease anxiety. So in a directional or one-tailed test, the hypothesis specify an increase or a decrease in the population mean. So let's take a look, see what this looks like. Okay, so same numbers. And same scenario. A researcher begins with the population, in this case, scores on a standardized test with scores normally distributed, mu 65, standard deviation of 15. The researcher suspects that special training in reading skills will produce an increase in the scores for the individuals in the population. So you see how there's a difference there? I didn't just say we'll have an effect, we'll have a change, right? But now I'm actually saying which way it's going to go. So we'll have an increase in the population. So a sample of 25 individuals is selected, and the treatment is given to the sample. Following the treatment, the average score for the sample is 73. Okay, so again, this is going to sound a little bit different than the first time. So the first time we just said, is there evidence that the training have an effect on test scores? But now it's saying, is there evidence that the training increases test scores? Same alpha though, 0.05. Okay, so this part should look really similar, right? So the null hypothesis mathematically, mean equals 65 in language. Special training and reading skills will not increase test scores. See, so note that direction stated. The alternative hypothesis, now this word gets a little bit different, right? Here, so mean is greater than 65. Okay? Or special training and reading skills will increase the test scores. Okay, same steps again. Find the standard error, find your z obtained. Right, use standard error as the denominator part of the z obtained. So you're going to get the same z obtained of 2.67, but this is where it gets a little bit tricky. Right? So now we're going to find our z crit. Now because we're doing a one-tailed test or directional, right, you just have to find the alpha 0.05, but you're going to dump it all into one side, so you don't need to split it in half. Okay, so now our z crit, that level, that water marker we have to beat, is only 1.645. See how it's a lot lower? Okay, p-value 0.0038. Okay, so we still have a z obtained 2.67. Okay, so is it significant? Absolutely, right? Special training significantly increased math scores. We reject the null hypothesis as z equals 2.67 and p equals 0.0038 with an alpha being still set at 0.05. So take a look what it looks like next. It's going to look a little bit different. See how we don't have another tail on this side? Because directionality, increase, decrease, greater, less than, more, less. Those kind of words are going to tip you into thinking that it's a directional test. Okay? So we have our alpha 0.05, we have 5% over here. Our z obtained is way over here. We reject the null. Okay. Some of the factors that influences hypothesis testing is the size of the difference between the sample mean and the original population. And this is going to usually be in the numerator of that z-score. Right? Variability, if the scores are all over the place, that's going to influence your hypothesis testing. Right? And it also influences, messes with your standard error and just the number of people you have in your sample. Right? Some of the assumptions that you have to keep with hypothesis testing: random sampling, independent observations, value of standard deviation is unchanged by the treatment, and you should assume that you're pulling a sample from a normally distributed population. Okay. There's some concerns with hypothesis testing. Some people think that we focus too much on the data, not the hypothesis, right? And the significant effects sometimes aren't that substantial, but most researchers rely on hypothesis testing. Effect size measures the absolute magnitude of a treatment effect independent of sample size. So it doesn't matter if I test on 1,000 people or 100 people. The effect size is going to measure that absolute magnitude of that treatment effect. Cohen's d. This is the first way we're going to measure effect size. Or again, so measuring that magnitude of treatment. You're going to take the mean difference, right, divided by standard deviation. And it's going to give you a number. If that number is around 0.2, you're going to say that that effect size is pretty small. So like 0.15, 0.23, 0.3, right? Those are all small. If your Cohen's d is around 0.5, you're going to say it has a medium effect size. This isn't a threshold. You don't have to get a 0.5. 0.48 still qualifies as medium, right? This is just like ranges. And if your Cohen's d is around 0.8, you're going to say it has a large effect size. Okay, so let's run it on our study. So we have mean, right, and we're doing our reading people again, mean of 73 with a mu of 65 divided by a standard deviation of 15 gives us a Cohen's d of 0.53. So we would say that has a medium effect size. Power. Power of a test is the probability that the test will correctly reject a false null hypothesis. It's kind of like a safety net, right? And usually you run power before you actually start the study. Okay? Power, how you find it is 1 minus beta, or 1 minus p, or the probability of committing a type 2 error. And what it's trying to do is going to try to detect if a treatment effect, if one exists. Okay? Some influences on power. As effect size increases, power also increases. Having a larger sample size will produce greater power. Right? Smaller sample size, smaller power. Reducing the alpha, so making it go from like 0.05 to 0.01, reduces power. And using a one-tailed test increases power, because what you're doing is you're making that alpha as big as possible. Okay? Again, please do your homework and email me or text me with any questions. Thank you.